Hello everyone, I'm Murat Kuscu, an assistant professor at Koç University. Thank you very much for joining us today, and I would also like to thank all the organizing committee for organizing this kind of workshop and inviting me as a keynote speaker. It's a great opportunity for me because this is the first time I attend a molecular communication workshop. I also couldn't attend any of those NanoCom conferences, so this is the first time I see such a focused community on molecular communications, and it's great to meet you in person. So today I will be talking about my recent research about towards getting practical with molecular communications. Maybe the title could be a little bit misleading because someone could imagine that I will be talking about practical applications, but this is not the case. I will be talking about practical testbeds mostly, and some of the findings that could be of practical relevance for molecular communications. I actually was thinking about another title, like getting physical molecular communications, but someone told me that that could mean something else, so I stick with this title today. So let's start. Okay, like this. Okay, we will start with a cat, but not now there. So I'm leading this Calico Lab, the Nanobiophysical Information and Communications Laboratory. And actually our laboratory takes its name from these calico cats. Maybe you know that, but probably not. These are the three colored cats, female cats. I like them very much actually. But of course our research has nothing to do with those calico cats or cats in general, but as for now, maybe in the future things will change. But right now we are carrying out interdisciplinary research at the intersection of nanotechnology, biotechnology, and the information and communication technologies. So this picture actually roughly summarizes what we are trying to achieve. This is Internet of Bio-Nanothings, right? So we are trying to create seamless communication interfaces between heterogeneous bio-nanothings, like natural biological cells, like engineered or artificial cells, or abiotic devices like nanobiosensors, right? So we are engineering interdisciplinary solutions to interconnect non-conventional bio-nanothings via non-conventional methods like molecular communications, and in non-conventional environments like inside human body, right? To enable non-conventional applications. So we use nanotechnology to build prototype molecular communication systems and testbeds, or transmitter-receiver architectures for molecular communications. We draw on biophysics to understand, model those molecular interactions at nanoscale, like ligand-receptor binding interactions, to optimize them from communication perspective. And the ICT is our main framework, of course, where we combine this nano and bio to enable those IOB-NT applications. So these are the IOB-NT applications that we envision, but I'm not going to go over them one by one because I assume everyone knows them very well, especially the smart track delivery and the continuous health monitoring, which attracted the most attention, right, in terms of IOB-NT. But the point is that we are not yet there, right? There is no any practical IOB-NT system deployment yet. But it would be great to have a classification of what we call as bio-nanothings, right? So I'd like to divide them into three categories. And the first category is passive molecular nano edges. Now these are primitive entities consisting of single or a few molecules, okay? They are not able to actively perform communication or any other function, but they require external stimuli. This could be like fluorescent molecules, like nanoparticles, other kinds of things. So once they get stimulated, they randomly start to exchange some sort of energy among each other. And the second category is abiotic devices, which are mostly based on nanomaterials like graphene. And of course, these are much more complex than the first one. They can actively actually energy harvest, right? Or they can perform computation, they might have some memory, and that they can communicate via several means, not just molecular communications, but other means as well. And the third category are biosynthetic devices. This could be engineered bacteria, artificial cells, etc. And the most important thing about them, they are inherently able to communicate via molecular means, right? So My recent research has dealt with all these three categories of bionanothings to varying extents. For example, I start my IUB journey with these passive molecular agents, like fluorescent molecules, fluorescent dyes. So we propose to use first resonance energy transfer, also known as FRET, as a means of information transfer. So this is a quantum mechanical phenomenon that describes the non-radiative and the very short range and fast energy transfer, excited energy transfer between fluorescent molecules. So we propose to encode the information into the excited state of a fluorescent molecule, and the information is transferred via this energy transfer method. So after a bunch of theoretical studies, we performed an experiment to practically realize a FRET-based nanonetwork. We used a MIMO configuration where several fluorescent molecules acting as transmitter and receiver nanoantennas. We had a laser source that excites those transmitter fluorescent molecules following an on-off keying approach, and we detected the fluorescence response of those receptor antennas via a fluorescence detector. And with this setting, we managed to transfer data at 250 kilobit per second rate. So to be honest, this experiment was of very little practical relevance or importance because we didn't come up with a useful application, maybe other than molecular computing, but we didn't study that. But it showed something important. It showed that the wireless nanocommunications at high data rates is possible, is feasible even between single molecular bionanothings. So when we start talking about more complex bionanothings like biosynthetic ones, abiotic devices, we can talk about molecular communications that we all know. The transfer of information via the exchange of molecules, just like the living cells communicate. So this is quite different, right? Radically different than conventional electromagnetic communications. So we need to approach it with multidisciplinary research tool sets. We already did a lot from theoretical aspects, like we developed many channel models for different scenarios. We developed detection techniques, modulation, coding techniques, etc. We developed simulation frameworks. We drive the theoretical performance limits of this communication method. But in doing so, we relied on so many simplifying assumptions about the highly complex, nonlinear, time-varying nature of the molecular communication channel and the unconventional nature of those transmitter and receiver architectures, right? And when we start building practical testbeds and start running experiments on them, we've seen that all those empirical results do not fit very well into the theoretical predictions. So we need to refine and revisit those theory, right? And in some of these experiments, we also see some unconventional phenomena that could be useful to develop new molecular communication techniques. So in the next couple of slides, maybe in the next 12 or 11 slides, we will review different approaches taken by different groups to develop practical testbeds for molecular communications before we see what we have done to this end. Okay. We will see that some of these testbeds purely rely on abiotic components, like nanomaterials, but the others also use biosynthetic devices as part of their testbeds, as a transmitter or receiver components. Okay. So as you all know, I assume, the first molecular communication testbed was developed by Andrew Eckford's group with a tabletop setting, and the transmitter was an electrical spray, right? And the receiver was an alcohol sensor, so the information carriers were IPA or alcohol molecules. And later they extended this testbed to accommodate for MIMO configuration, and this time they use spray nozzles as the transmitter antennas of this MIMO configuration. And another testbed was developed by Andrea Goldsmith's group. This was a fluidic testbed with a silicon tube acting as a channel with water inside, okay? And the peristaltic pumps were pumping hydrogen ions or protons in acid or base solutions to encode information into the channel, and the receiver was, of course, a pH sensor, pH probe, a microscale pH probe. And a similar testbed was developed by Nasiri-Kenaris group. Again, the information is encoded into the pH of the environment. The receiver was a pH meter, pH sensor, but the transmitter was a solenoid, electrical solenoid that controls the transmission of those hydrogen ions into the channel. And the channel was a little bit larger than the previous one. It's a plexi pipe. And rather different approach was taken by Nunzio Tuchito's group, right? This time the molecules, the information carriers was fluorescent nanoparticles, and the transmitter is a syringe pump, the receiver, the channel is a microfluidic tube, and the receiver is a scanning fluorescent detector that decodes the messages based on the fluorescence these nanoparticles emit. And Robert Schauber's group used magnetic nanoparticles as information carriers. The transmitter again is a syringe pump, and they use a microfluidic tube as a channel, but the receiver is a little bit different. This is susceptometer that detects the magnetic field of those nanoparticles to decode the transmitted molecular messages. And in the meantime, Alan Marshall's and Stephen Taylor's groups developed this odor-based macroscale molecular communication testbed. The transmitter this time was a custom-made odor gas generator, and the receiver was a mass spectrometer that distinguishes molecules based on their mass-to-charge ratio. So this testbed allows transmission and reception of multiple types of molecules at the same time. Okay, yet another testbed uses fluorescent molecules, fluorescent dyes, as information carriers. Not remember the name, but Mr. Hoe's group, Peter Hoe's group, developed this macroscale air-based testbed. The transmitter was electrical sprayer, industrial sprayer that sprays the water-based solvents of fluorescent dyes, different types of fluorescent dyes into the channel, and the receiver was a camera-based fluorescent detector. And similarly, Gua's group developed this macroscale testbed. Again, the information is encoded into the concentration of fluorescent molecules. This time the channel was a fluid dynamic channel. So that is quite different than this one. Actually, this was air-based and this was fluid-based. And the receiver was a laser and a camera-based fluorescent detector. Now, as I told you, there are also molecular communication testbeds that use biosynthetic devices as transmitter or receivers. For example, Robert Schauber's group developed this testbed where they use engineered E. coli bacteria as a transmitter that can pump hydrogen ions or protons when stimulated with light. So they encode the information into the pH of the environment, and that information is again detected by a pH sensor. Similarly, in another study, Nasiri-Kenaris group used E. coli bacteria, engineered E. coli bacteria, but this time as a receiver that can respond to some sort of molecule like L-rhamnose by expressing green fluorescent proteins whose concentration can be detected by a fluorescent detector. So they developed this microfluidic chip where the information carrying L-rhamnose molecules are supplied through one inlet, and they propagate to the receiver chamber that contains this GFP expressing bacteria. Now, as we see, there are many different approaches taken by different groups to develop these testbeds, and these testbeds have been really useful to refine the theory, to develop more accurate channel models, or develop more practical molecular communication techniques. But there are many rooms for improvement, of course. For example, instead of off-the-shelf components, commercial components, if we have more control over the design of these individual components, like transmitter, receiver, or channel, we can optimize them from communication perspective, right? And likewise, we can devise custom designed components to test wide range of molecular communication scenarios if we have control over their designs. And we also need higher spatial temporal control over the propagation and the transmission of those molecular signals so that we can test the performance of modulation detection techniques more accurately, right? And the scalability to micro-nanoscales of these components is another issue, especially for transmitter-receiver components. Otherwise, we already have microfluidic channels that are in the microscale. And if you look at these testbeds developed so far, we'll notice that the focus is particularly on the propagation of molecular communication signals, maybe except for the biosynthetic ones. But we might be missing a lot of important molecular interactions, like ligand-receptor interactions and their effects, which can be both a challenge for us and an opportunity for molecular communications on IOP end. So as an alternative, we developed a receiver-centric molecular communication testbed, which is not able to solve all these problems I mentioned, but takes an important step forward, I guess. So this is the diagram and the picture of our testbed. We use, again, a commercial microfluidic pressure controller as the transmitter, and we had a microfluidic chip that contains the molecular communication channel and the receiver, a field effect transistor-based DNA biosensor as the receiver at the bottom of this channel. So we use DNA molecules, single-stranded DNA molecules, as the information carriers in this testbed. So if we take a closer look at the transmitter, we use the microfluidic components produced by Alflow, which is a French-based company. And the microfluidic chip was made of PDMS polymer, and we use these 3D printed molds to shape those microfluidic channels inside. And for the receiver, we use field effect transistor-based biosensors, also known as biofrets, that can convert those chemical signals into electrical signals. And now in the biofrets, the binding of these ligands, which are the information carriers or interferers, to the surface receptors on the surface of this transistor, modulates the channel conductance, the transducer channel conductance. So the output current becomes a function of the input ligand concentration. So this is our receiver in the testbed. And we decided to use graphene as the transducer channel, as the sensing material, because of its very high sensitivity, exceptional properties like two-dimensional structure, or the flexibility. So at the Cambridge Graphene Center, we first developed a graphene field effect transistor, not a biosensor yet, by using monolayer graphene produced by chemical vapor deposition technique on a silicon substrate. And then we integrated this PDMS microfluidic chip with this transistor, and then we performed the biofunctionalization. Biofunctionalization of DNA-based receptors on the surface of this transistor so that it became a biosensor. So these receptors, the single-stranded DNA molecules, are complementary to the information carriers. So they hybridize with each other complementarily. So it gives our receiver a high level of selectivity, actually, in the case of interfering molecules in the channel, for example. So this was our experimental setup again. The microfluidic pressure controller modulates the injection rate of these information carriers and the buffer solution into the channel, and it is detected by our receiver at the bottom of the channel. So we first determine the sensogram of our receiver to determine its sensitivity towards information carriers. And we detected that it can detect concentrations down to 50 nanomolar, which is not very good, but it's fair. And then we test its selectivity in the case of interferer molecules, which are also DNA molecules, but with different base sequences. So they don't complementarily hybridize with our receptors. And we've seen that our receiver is fairly selective as it doesn't respond to the non-complementary targets as it responds to the complementary one. To determine the time-varying response, we applied 1 micromolar DNA concentration with varying pulse durations. For example, this is the result for 30-second pulse and the 60-second pulse. And then we fit these results into a theoretical model that we previously developed. And as you see, they seem to be in good agreement, although the model's accuracy is a little bit low during this return phase. It's the dissociation phase, as we will talk. Then we performed communication experiments by encoding the information into the concentration of DNA molecules following an on-off keying approach. We send a pseudo-random binary data with varying bit intervals, and we've seen that there is a huge intersymbol interference, especially for small values of bit intervals, so that the receiver is not able to return to its baseline current. So applying a constant threshold for decoding this binary message will likely to fail, right? So instead we applied a difference-based detection technique, which just compares the electrical currents between consecutive bit transmissions. We still observe a couple of errors, which doesn't follow a consistent pattern actually, but it can be improved by applying a better noise cancelling filters, I guess. We didn't work on that very much. But the point is that the data rate is very low, as you see. It takes like hundreds of seconds just to send 1 bit of information, right? That's a huge problem for molecular communications and for our testbeds. So leaving that aside for now, what are the problems, general problems with this testbed? Let me drink some water. So we first have a problem with the transmitter, as you see. We were using microfluidic pressure controllers to modulate the injection rate of information molecules into the microfluidic channel, but we don't know exactly what gets inside into this channel, how we shape those pulses through this Y-shaped entrance. Okay? So unless we know that, we cannot optimize our system from communication perspective. We cannot accurately evaluate the performance of modulation detection techniques, right? So to resolve this problem, we turn our attention into microfluidic pulse shaping techniques. And these hydrodynamic pulse shaping methods are our first target. They are just using the interplay between hydrodynamic forces that are provided through different inlets to create chemical waveforms inside microfluidic channels. So for example, we are now working this hydrodynamic gating method, where the information molecules are continuously supplied from this inlet, are switched on and off through the gate flow supplied through this inlet, the other inlet. So this method, we show that through console simulations, is able to create very short concentration pulses inside the microfluidic channel that could be used to create other types of pulse shapes as well inside the microfluidic channel. What about the receiver, which is the main component of our testbed? Now, if we look back at the time-varying response, we already discussed, but it takes a lot of time for the receiver to return back to the baseline current. So this is actually not expected in convection diffusion channels, right? Because the molecules in the channel are very quickly purged from the channel. So there are no molecules left inside the channel, right, microfluidic channel. So this implies that the problem is related to the receiver. And actually, it's caused by the low dissociation rate of those molecules from each other, low dissociation rate of the hybridization process. So we turn our attention this time to ligand-receptor binding interactions to understand the effect of these interactions on the molecular communication performance. And by the way, these interactions are not only critical for our testbed or for biosensor-based molecular communication receivers, but also for biosynthetic devices, because these interactions are commonly utilized by biological cells as an interface with the environment for sensing or communication purposes, right? Now, in the biosensing or let's say drug design context, we want these interactions to be very strong, right? We want to increase their affinity, increase the kinetic parameters, etc. But this is not the case in molecular communications. Because if these two molecules, ligands and receptors, bind very strongly, with very high affinity, and with low kinetic reaction rates, they will stay bound for a very long time. So we will not be able to detect the succeeding messages without any interference, right? So that's a problem. And this will, of course, ultimately lower the bandwidth of the communication, which is already limited by the Lopez characteristics of the molecular communication chain. And bandwidth, as you see, is not the only parameter that is related to interaction parameters, but also we show that the sensitivity of the receiver, selectivity, dynamic range, which is important, and also the noise characteristics of the receiver are all strongly correlated with these interaction parameters, kinetic rays and the affinity of ligand-receptor binding interactions. So all these trade-offs actually point to a multi-objective optimization problem regarding these interactions. And these interactions bring lots of challenges, but they also bring opportunities for molecular communication system design. So we are now at the age of de novo protein design, synthetic receptors, optimers. We have the tools to tune these interaction parameters, their kinetic rays and affinity. So they can open new ways to develop new modulation detection techniques for molecular communications, or create adaptive molecular communication networks, exploiting those ligand-receptor interactions, or address the multi-access or coexistence problems in crowded molecular communication networks. Now, in the next couple of slides, I will try to convince you that these interactions can be exploited to develop new molecular communication techniques. For example, we are now working on this frequency domain detection technique, which is not published yet, but we are getting some results. This technique exploits the fact that different ligand-receptor interaction rates, different interaction rates of different types of molecules with the same receptors are reflected to the power spectral density of the binding noise or the binding fluctuations as different cutoff frequencies, as you see here, the banding curves. So for example, this cutoff frequency is caused by information molecules, and this is caused by another type of molecule, interfering molecules, both interacting with the same receptors. And through some simulations, we show that a detector, a molecular communication detector, performs much better compared to a time domain detection in the presence of interfering molecules, if we exploit those frequency characteristics. And this advantage over the time domain detection becomes more prominent when this interference drives the receiver into saturation. So the time domain detection technique, when comparing those different levels in the saturation case, will perform very poorly, but in frequency domain, we are still able to determine the difference between information and interfering molecules through this frequency domain pattern. Now, in the case of biosynthetic devices, like engineered bacteria or artificial cells, we have access to the states of individual receptors, their bound, unbound states, the complete history of their binding process. And we show that these bound and unbound time durations, the bound ones are denoted by this green line and the unbound ones are this red line, provide much richer information compared to the instantaneous number of bound receptors, of course. For example, the bound time durations are directly informative of the concentration ratios of different types of molecules in the channel coexisting. And the unbound time durations are informative of the total ligand concentration. regardless of their types, actually. So we combine these two statistics, bound and unbound time durations, to develop a channel sensing technique. Or I like to call it spectrum sensing, but I will not discuss about that actually. So this channel sensing technique is able to detect the individual concentrations of different types of ligands in the channel at the same time. And it's very important for biological environments because they are full of different kinds of molecules, interferers, that can interfere with the binding process. They can bind the same type of receptors. And in that case, our receiver is able to detect the concentration of interferer and avoid the interference at all, actually. And this technique can also enable multiplex communication to boost the data rate with different types of molecules. Or it can enable multi-access in crowded molecular communication networks. So for all these techniques, we are also developing synthetic receptor designs and the chemical reaction networks that can detect, that can sample these bound and unbound time durations and perform the arithmetic operation required for this detection technique. For example, in another study, we focused on ratio-based modulation, which was actually proposed by another group like 9 years ago, but apparently no one studied this technique later on. I don't know why, but this technique is quite simple. The information is just encoded into the concentration ratio of two different types of ligands. Okay? And it can be quite robust, actually, against the dynamic channel variations. Dynamic variations in the transmit power or the variations in the channel impulse response. As long as these variations affect both types of ligands at the same rate. So the ratio stays the same, whereas the concentration can change. In the case of mobility, for example. So the concentration changes, but the mobility pattern affects both types of ligands if they have the same diffusion coefficient, the same way, the same rate. So what we did is actually show that by only sampling the bound time intervals of the receptors with very practical technique, we can detect the concentration ratios very accurately. And we calculated the channel capacity, end-to-end channel capacity with this modulation and detection technique, and then compare it to CSK, concentration shift keying modulation, for the case when the transmitter is power limited. So the maximum number of molecules it can transmit is limited. And we've seen it brings huge advantages in terms of capacity. And lastly, these ligand-receptor interactions can be exploited to enable adaptivity for molecular communication receivers. Now, there are many biological mechanisms like this allostery or cooperativity of receptors that can actually dynamically tune the interaction parameters of these receptors. So if we, for example, can tune the dissociation constant of ligand-receptor interaction for some specific type of ligands, information molecules, we can change the dynamic range and the sensitivity region of our receiver. And this is very important for dynamic channel conditions in molecular communications. And we simulated a case where there is an interference of same type of molecules whose concentration can take a random number at every time of transmission, at each time of transmission. And we showed that by comparing this non-adaptive case, non-adaptive receptors, fixed dissociation constants, to a case where the receiver can adjust the dissociation constant dynamically, we show that it brings huge advantages in terms of bit area probability. All right, I don't have any conclusions, but I like to point out that all this interdisciplinary work towards practical molecular communications can actually have far-reaching impact on many different areas, like microfluidic drug delivery, right? Microfluidic pulse shaping can have impact on that area. Or biosensing for dynamic biomarkers, this is not studied very well actually in the literature, in the biosensing literature. We are still working with constant levels of biomarkers, but when the case becomes dynamic, our studies towards molecular communications can play a significant role in that. Or multiplex biosensing, sensing of different types of biomarkers at the same time. The channel sensing technique we develop has a direct impact on that method, for example, or the frequency domain detection technique, right? So we are a new group, actually, with a few PhD students and master students. It's been just 2 years, and we are wide open to interdisciplinary collaborations. That's the last thing I want to say. If you have any questions, I would like to answer them. Thank you very much.
So, thank you for the talk. I think we don't want to do this so formal because we're not a huge crowd. Are there any questions for Murat? Or is everything answered? Everyone would like to know.
Yes, please.
Okay. Nice to meet you.
Thank you, please.
I read a lot. This is the first time for me being this year, so nice to meet everybody.
Thank you. Our pleasure.
I think that the main message that I will take home from your talk is the threshold that we have between selectivity and reversibility of the interaction between the molecule and surface that you have. Do you have any information or any experience on releasing some other molecules that helps after the interaction the molecule to be detached from the surface? Because that's a chemical interaction. Of course, if you have a single strand DNA and you use the perfect matching DNA single strand, it will bind. And it is being synthesized to be bind and touch. But you can put some another molecule, for example, EDTA, and then this can be opened and flow away. So my question is, do you have any experience of this, or do you expect if you start to release something to attach, something to detach the system from the receiver?
Yes, that's a perfect question. Actually, I researched about that when I was doing my PhD, trying to come up with adaptive receivers, like releasing, as you said, some sort of enzyme that can detach so that we can increase the data rate so they will not stay bound for a long time. Or there are other mechanisms as well. I did a little research, so I cannot say a lot about that, about those mechanisms, but I know that there exists some. But there are also other mechanisms that is suitable for abiotic devices. Like we have a biofet, right? We are applying an electrical signal. So DNA molecules are negatively charged in those physiological conditions. So if we change the polarity of the electrical signal we apply to the channel, transducer channel, we can actually change the conformity of those DNA molecules, and they can detach quite easily. So that kind of techniques exist in the biosensing literature, but it's not studied often, as far as I know. But it's a good direction to address. Thank you for this question. Yes, any other questions or comments?
I can go. Yeah, I was also going to ask, I guess, about if you were aware of strategies for tuning the dissociation rates, but I guess that would align with what you were just describing, being able to do this in these biofet systems. So perhaps I'll go to another question then. So looking at, when you were describing having knowledge of the history of the binding of the individual receptors, to apply the detector design that you had done, did you actually need to have the full individual history in the sense of, you know, that receptor 1 has these bound and unbound times, receptor 2 has these bound and unbound times? or were you able to aggregate that and say, was like, did you really need the full information, or were you able to summarize that for the actual solving the optimization problem?
No, we don't need the full history. Actually, that's been being done by another professor in Australia. Maybe Malcolm, you can remember his name. Chung-Tun, Professor Chung-Tun. He's using the full history of a single receptor, for example, applying some sort of Bayesian techniques to decode the information from the continuous history. What we are doing is just a sample at some sampling activation time. Here you see, we start this activation, the sampling process, and we take only one unbound time interval or a bound time interval from each receptor, and those receptors are independent. So we collect, for example, NR number of unbound time intervals, and we just use them. So this is a very short sampling. We are not exploiting all the continuous history, but of course that would carry much more information, but the process becomes more complicated for synthetic cells.
So how are you able to measure that at an individual receptor level? Is it just the nature of the test bed that you have enables you to do this, or is that something that's
no,
practical to do?
This is not part of our test bed actually. This is the theoretical part of our research, but these synthetic receptors that can sample the bound and unbound time intervals, like you see a diagram here, this exploits the kinetic proofreading mechanism that's already being used by T cells to discriminate between different types of molecules very accurately. So why I call this practical is that it's being utilized by biological cells. So we are just modifying that structure for future synthetic cells or synthetic receptors. For example, this includes a multiple bound and unbound states, as you see, with the different transition rates. Depending on the type of molecule, the interfere molecules, for example, stay very short, right, in the bound state, and the information molecules are expected to stay longer. So this KPI mechanism, by giving multiple states with constant transition rates, can discriminate between these different periods of binding. So interfere molecules, for example, will drop in this zero state because it will unbind very quickly, but the bound or the information molecules stay bound longer so that it will excite this state as well. So that's a very simple KPI mechanism. But it's not a part of our test bed. We are not still.
Sure. Yeah, I was just curious to what level you were requiring information and whether you had a test bed to measure at that level. For, I guess, just going back a couple of slides, looking at this DNA binding scheme, were you having issues with, or did you see like a full saturation of the receptors that you had, or was the receptor density sufficiently high that wasn't a concern?
So as far as we realize, we do not experience the saturation in these experiments. Because in the case of saturation, as you see, the level is changing very slightly actually. It's just dropping from 1 to the 0.98 in terms of electrical current. Probably we are not able to measure the receptor concentration actually. Maybe we can do that in the future using some Raman spectroscopy techniques. At the moment, we are not sure if this goes to the saturation or not, but probably it didn't go to the saturation level. So we can actually see the full response curves, but the problem, as I told you, is going back to the baseline curves.
Right. Was there much, I guess, the system that you were, where you were doing these tests, it was a fully synthetic in the sense it was a microfluidic platform that you had built. So the DNA that you were using was DNA that you had made yourself, or was it off the shelf, or it came from some source?
They're off the shelf. We designed the base sequences, we sent to the Sigma 3, and they sent us back.
I was just wondering if you had a problem with getting like DNA fragments Like how many base pairs would your symbol be?
Yeah, actually it was like 17 base pair or 14. I don't remember the exact number, but that was no problem actually. It was a smooth process.
Okay.
We just designed through the sigma-Aldrich interface the base sequence. Okay, the base sequences are written here. Actually, it is like 18 bases in each DNA. For example, we ordered interfering DNAs, non-complementary DNAs, by changing just one base sequence on that, or in that case, like 7 base sequences. So it was a quite easy process.
So you didn't have a problem with fragments of just like, for example, the GCA portion as a fragment, like binding and then blocking, like being an interference then for the full sequences that you were using.
Well, actually, we don't have those details because we are not able to detect what's going on the surface.
Okay.
So we just apply some concentration and just measure the electrical current. But there are ways to measure that as well. For example, we were planning to attach fluorescent probes to see the distribution of bound molecules over the surface. And that could actually reveal more information, whether there is a problem with the binding, a blockage, etc. This process is a little bit complex. For example, we identified that the receiver surface is not fully covered with DNA molecules. So some of the DNA molecules directly attach to the receiver surface, which creates an interference. This is not wanted in our testbed, right? We want it to be selective, bind to the receptors. So they also transfer their electrical charges and affect the output currents. And this is hard to eliminate actually. For that, we are planning to use better linker molecules that can attach to the surface completely, cover all of them. This linker, for example, was P-based, but there are other linkers that can attach more strongly to the graphene channel. And we hope to improve these aspects in our test bed. There are many things actually that should be improved.
Lots of work to do.
Yeah,
That's good.
Yeah,
That's good.
Exactly.
Well, thank you very much.
Thank you very much.
Thank you.
It was nice questions.
Okay, are there further questions? I think Sebastian has one.
Yeah.
I guess I have one more question. So in your test bed, you basically, I mean, you sample at a relatively high rate, I think, right, the receptor state. So I was wondering, like, could you imagine any mechanism which could be used to integrate the receptor binding information locally and then like read it out at a lower sampling rate? So, I mean, my question is basically if you imagine this as a biosensor, like in-body application, whatever, you would probably query it at a lower sampling rate, right? I mean, not instantaneously or such. So could there be like a local mechanism to store somehow the binding information?
It's like a sensor with memory, right?
Yeah, exactly. Yeah.
I guess there are such structures like memristor-based biosensors that can store that information for a while. That could be actually a nice pathway to attack the intersignal interference, for example, because we use memory, right, to avoid intersignal interference most of the time.
Yeah. Exactly.
I'm not sure if that is your question, but.
No, I mean, yeah, it was basically inspired, like if you look at this receptor, ligand binding receptor systems in nature, you often have some integration process at the receiver, right? So basically to acquire information beyond the instantaneous statistics. So I was wondering if you, for the synthetic scenario, if you had something in mind which would go into a similar direction.
Yeah, I understand. That's very hard to realize in abiotic devices actually. Maybe memristor could be a solution, but that's not actually matching what we are saying, right? In biosynthetic devices, in biological cells, those integration happens so that they can detect the information more accurately. But it's very hard to realize in, I guess, in biosensors like this, because we get the a cumulative result of the binding process. We don't have access to individual receptors, etc. I can't imagine of any way to do that at the moment, maybe other than memristors, as I said.
Yeah, okay, thanks. Yeah.
But that's a good research problem, I guess. Thank you very much.
Oh, yeah, thank you. Yeah.
Okay, are there further questions? If not, let's thank Murat again.
Thank you.